Ever wonder how your computer always seems to know the right time? It feels like such a simple thing, right? But the answer pulls back the curtain on this incredible, hidden global system that keeps our entire digital world ticking in perfect sync. So let's dive in.
I mean, think about it. You can shut down your laptop, unplug it, stick it in a drawer for a week, and when you fire it back up, bam, the time is somehow still correct. How is that even possible? No power, no internet connection. What's the secret?
Well, the first piece of this puzzle is actually hidden deep inside the hardware itself. You see, your computer doesn't just have a brain, it basically has its own tiny personal watch that's always on.
And honestly, this analogy from Reddit user Tritonice just hits the nail on the head. It's the perfect way to picture it. Just like the watch on your wrist, your computer has a dedicated little component whose only job is to just keep counting the seconds, completely separate from everything else. So that little power source, it's called the CMOS battery. It's usually one of those little coin-sized cells, and it feeds a constant, tiny trickle of power to two really crucial things. First, the real-time clock, that's our digital watch, and second, the BIOS, which stores all the super fundamental settings, like which hard drive to boot from.
Oh, and you definitely know when this battery dies. All of a sudden, your computer's clock will reset itself to some random default date, like January 1st, 1970, every single time you turn it on. It forgets its own settings, it throws up weird errors when it starts up. It's such a tiny part, but man, is it important. Okay, so a local clock solves part of the mystery, but let's be real, that little clock isn't perfect. Over time, it's going to drift a little. So how does it stay so precisely in sync, down to the millisecond, with literally billions of other devices all across the globe? Well, the answer, as you probably guessed, is the internet. The moment your computer gets online, it reaches out and plugs itself into this massive, worldwide timekeeping system. This whole global sync-up is managed by something called the Network Time Protocol, or NTP. And get this isn't some fancy new tech. It's one of the oldest internet protocols still in use, designed way back in 1985. It's practically part of the internet's DNA. And it all happens over its own special channel. You can think of it like a dedicated private lane on the internet highway, just for time. All of these NTP messages travel back and forth through something called UDP port 123. It's the universal address for asking, hey, what time is it? But what is the correct time that everything is trying to sync to? That benchmark is called Coordinated Universal Time, or UTC. Now, it's really important to get this. UTC is not a time zone. It's more like the master clock for the entire planet. It's the ultimate source of truth that all our different time zones are measured against. Right, but that just leads to another question, doesn't it? If UTC is the master clock, where does it get the time from? Well, it turns out there's a very strict hierarchy, a pyramid of precision, that makes this all work. This hierarchy is called the NTP stratum. And stratum level is really just a fancy way of saying how many steps, or hops, a server is away from the most ridiculously accurate clocks in existence. The lower the stratum number, the closer you are to the original source. So here's how that pyramid is built. At the very top, you have stratum 0. These are the sources of truth. We're talking atomic clocks, GPS satellites, the most precise things we have. Then, stratum 1 servers talk directly to them. Stratum 2 servers talk to stratum 1, and so on down the chain. Your computer? It usually connects way down at a stratum 3 or 4 server, and that's by design. It spreads out the requests so no single server gets overloaded. For most of us, NTP is ridiculously accurate, down to a few milliseconds, which is amazing. But in some fields, like high-frequency stock trading or scientific research, even that is too slow. There's another standard, the Precision Time Protocol, or PTP, that can sync devices down to a nanosecond. That's a billionth of a second. Just mind-boggling. Okay, so this is where things get really, really weird. What happens when our perfect, mathematically consistent atomic clocks crash head-on with the messy, slightly unpredictable reality of our own planet's rotation? See, here's the thing. We're really dealing with two different kinds of time. On one hand, you have atomic time, or TAI. It's flawless, based on hundreds of atomic clocks, and in its world, a day is exactly 86,400 seconds. But then you have universal time, which is based on the Earth's actual rotation, and our planet, it wobbles. It's slowing down, An average solar day is actually about 2,000ths of a second longer than our perfect atomic day.
So to keep our official time, UTC, lined up with the actual sun in the sky, we basically have to cheat. Every so often, the world's timekeepers declare a leap second. For 1 minute, the clock will go from 23:59:59, not to the next hour, but to 23:59:60. Then it ticks over. We literally create a 61-second minute just to let the wobbly Earth catch up.
And this isn't a one-time thing. Since this whole system started in 1972, we've had to do this 27 times. When you add that to an initial 10-second difference, it means our official time today, UTC, is now a full 37 seconds behind pure, unchanging atomic time. It's wild. And you can probably guess this is a total nightmare for computers. They are built on the beautiful, simple assumption that every single day has exactly 86,400 seconds, period. When a leap second happens, some systems just freak out. Back in 1998, for example, some systems just repeated the timestamp for that extra second, meaning one moment in time could have 2 different digital records. That's a huge problem.
So this constant fiddling with time, this fudging the numbers, has created some massive headaches for the tech world. And it's forcing us to ask some really big, fundamental questions about the future of time itself.
And these little timekeeping quirks can lead to some very real risks. You've probably heard of the Y2K bug, but have you heard about the year 2038 problem? A lot of older systems count time as the number of seconds since 1970 using a 32-bit number. Well, on January 19th, 2038, that number is going to run out of digits. It's going to wrap all the way around, and the computer will suddenly think it's 1901.
It's really helpful to think of it as a sequel to the Y2K bug. With Y2K, the issue was using just 2 digits for the year. For 2038, the problem is a 32-bit number, just running out of room. Now, the good news is most modern systems have already been fixed. They use 64-bit time. But there are a lot of older, embedded systems out there that could still be vulnerable.
Because of all these problems, the bugs, the crashes, the uncertainty, there's now a huge global push to just simplify things. In fact, a major international body has already voted to get rid of the leap second entirely by 2035. The idea is to just stop correcting our clocks and let them slowly, gradually drift out of sync with the Earth's rotation.
And that leaves us with this incredible dilemma, right? Do we prioritize technological simplicity and just get rid of the leap second to make life easier for our computers? Even if that means hundreds of years from now, noon on our clocks could be happening when the sun is setting. It's a huge decision about the very nature of time itself, and we've got about a decade to figure it out.